Okay, so when I was looking at operations that we can do with vectors, we had that we can add and subtract vectors. We can multiply vectors by a number, but I didn't say we could multiply vectors with a vector. There are two common ways to multiply vectors with vectors. One of them I'm going to look at in this video, and that is the dot product. Let's define two vectors. Okay. The dot product of these two vectors is calculated as such. So we have the dot product is the sum multiplying element-wise the components. This is how, out in the wild, you give me two vectors, this is how I would take their dot product. But the dot product also has another meaning, and that is it's also equal to the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. Because if we take these vectors as direction vectors, there will always be an angle between them. Even if we do it in 3D, and even if that angle isn't a nice angle, there is always an angle between them. Okay, so just in a practical standpoint, there's a number of important sort of cases here to consider. If these two vectors are orthogonal or perpendicular to each other, those are two words which mean the same thing, then this implies that the angle between them is 90. That's equal definition. Well, I mean, yeah, fine. Okay, that's all right. And this means that their dot product will be 0. Now, does the reverse hold? If the dot product is 0, does that mean that these two are orthogonal? Not necessarily. Like a lot of things in math, it could be a cheap trick. Okay, so the three cases are they're 90 degrees, they're orthogonal to each other, or one of these input vectors is the 0 vector, it has no length. So we need to consider that as well, but in practical terms, it doesn't often come up. Now, other cases to consider, if the angle is between, if it's acute, so it's between -90 to +90, not including either endpoint, then the dot product is bigger than 0. If it is, I'll just say, let me go the other way, sorry. Let me go, so what I'm doing is I'm sort of making a discontinuity here, and I'm saying, okay, this is 0 degrees, -90, +90, and there's a discontinuity here because we have 180 degrees, -180 degrees. Okay, so if theta is anywhere between -180 up to 90, union with 90 up to 180, then that implies that the dot product is less than 0. But long story short, think of it in terms of front faces and back faces. So if we have, let me pick one vector here, and then another vector could be anywhere on this range or on this range. This will produce positive dot products because the vectors are kind of facing the same direction. If the vector is up here, that's a 0 dot product because it is exactly 90 degrees. And if the vector is on the back side, then that will produce a negative dot product compared to this vector. That's a messy diagram. But anyway, let's step in and have a look at the Python. Oh, sorry. There's one more thing. If that angle is 0, then that implies that the dot product is simply equal to the product of norms, because, well, cosine of 0 is 1. So we have the product of norms times 1. Okay, and this gives us another result. This gives us that the magnitude of u squared is equal to u dot with itself. And then we have the fact that the dot product is a linear operator, and so the dot of a vector with a sum of vectors is equal to the sum of dots. So we have u dot a plus u dot b. Now we have the mechanism to prove the triangle inequality. So remember, the triangle inequality states that u plus v is less than or equal to the individual norms. Okay. Let's start with the left-hand side and then the right-hand side and compare them. So we'll go u plus v squared. That is the dot of u plus v with itself, which, again, like I said, it's a linear operator, so it's the same as this dot summed together. And then we can split those brackets again. And then we can say, okay, we'll just rearrange things a bit. We know that u dot u is magnitude, the norm of u squared. We know that order of dot product actually doesn't matter, so we'll just call this 2u dot v. And then we'll have magnitude of v squared. So that's the left-hand side of this expression. Let's take the right-hand side of the expression and square it. That, and we just do binomial expansion, because remember, these are just real numbers, so we have magnitude u squared plus 2 magnitude u magnitude v plus v squared. I'm being a little lazy with my tildes. They're all there. Imagine the tildes are all there. Okay, and now if we compare this line to the line above, well, this expression here can be positive or negative, and this expression here, because we're taking the norms of those vectors, can only be positive. Just double checking that. And this is a well-defined, because remember, this operation will produce a real number. I was just saying, yeah, okay, good. So what we get is, as a result, we have that this left-hand side, the square of it is less than or equal to the square of the right-hand side. And then applying the square root to both sides, we then get our result. Okay, and we can't sort of take this line and manipulate this line ahead of time, because that would sort of be assuming the thing that we want to prove, kind of. Anyway, we're doing it this way. All right, so there it is. There's a proof of the triangle inequality. Now let's jump in and have a look at the Python code. Okay, so I'm just going to adjust these so they have the same dimensions. Actually, I'm not going to do that. We'll go numpy dot. We have two vectors to take in, so we'll take in u and v. V and u doesn't matter. And then we'll print the dot product. Okay, and before we do this, let's check it. So I would expect the dot product to be element-wise 1 times 1 plus 2 times negative 1. So 1 minus 2, I would expect minus 1 is my result here. Let's check that. Yep, minus 1. That's looking good. Okay, now let's come up with a case where these are orthogonal to each other. So we'll have just 1. So each has a component of 1, but they're in independent things. So this is the x-axis and this will be the y-axis. The x and y-axis are orthogonal to each other. We run that, we get 0. Okay, that's all very exciting. What about some non-trivial examples? So if I have 1 and 4, so think of this like a direction. For 1 unit across, we go 4 units up, okay? What is the opposite direction to that? It is, if we go 1 unit across, we go negative, I want to say negative 4, but if you imagine two lines, if line A gets really steep, line B should not be equally steep. It should be sort of shallow as well. So we'll go negative 1 over 4. And these two vectors should be orthogonal to each other. Run that, and we get 0. Awesome. So yeah, let me do the triangle inequality example. So we'll go u plus, oh, that's a bit much. Okay, we'll go okay, and then I'll say, all right, let's go norm 1 is length of w. Okay, so we'll compare these. We'll go print the left-hand side. Yeah, I mean, that makes sense. That makes sense. So the left-hand side, the sum, it has a length of 4.25. The right-hand side has a length of 5.15. So that's just an example of the triangle inequality. Anyway, hope you enjoyed that. And yeah, I'll see you again soon. Bye.